we continue with the second keynote, Dr. Martin Schneider on alternative fuels in cement production. Yeah.
Yes. Thank you very much for the nice introduction. Can you see my screen? Full screen?
Yeah, see your screen.
And you can hear me loud and clear. That's
we also
very
hear
nice.
you.
Yeah.
Yeah.
So for me, it's very easy as a second speaker because Hubert Grech has already, given a great introduction into the use of alternative materials in cement and clinker production. And I have to say that in our country, in Germany, situation is quite similar when it comes to input parameters. The philosophy is the same, to make sure that we have a really sound and environmentally friendly use of alternative materials in the cement production. Now, and I was asked, to give a different view, but you will see that the linking element are the alternative fuels here. A different view on the cement production, namely looking at cement making from the CO2 point of view. You all know that we are under, I really have to say, under high pressure to really lower our CO2 emissions. And the reason is, let me just get my mouse here. So the reason is, as you all know, there is a global acceptance for good reasons, and it's good that we have to fight climate change. And you may remember that the Paris Convention started with aiming at a 2-degree limits in the temperature increase globally, and also that has been adapted and further developed into a 1.5-degree scenario for very good reasons. I think I don't have to bring this back into your mind. And the question is, what is the position of the cement industry? How are we addressing this? And at the final point, of course, what kind of role are alternative fuels playing here? Now, those of you who are familiar with cement manufacturing, and I've seen in the audience quite a few familiar names, and I think I should not tell you too much about this, but maybe just to remind you that cement production is based on raw materials which contain calcium carbonate, because our main raw material is limestone and some degree clay. And as you all know that we need this limestone in order to form the clinker phases, which at the end are responsible for the strength development of cement when you mix it with water. So I think it's a unique mineralogical process, and the chemistry behind requires limestone. We need this calcium oxide, and in order to come to calcium oxide, we have to burn the raw materials in order to produce clinker, and under these conditions, we have CO2 being released. So we have, as a rule of thumb, we have 2/3 of our emissions coming from the raw materials, basically from the decarbonization of limestone. And we have roughly 1/3 of our fuel emissions, coming from the combustion of the fuels. This is a rule of thumb, it varies a little bit, and I will come back to this later. Now, if, like in many other sectors, if we were able to, for example, electrify our kilns, which is still far a long way to go, if theoretically we were able to reduce fuel emissions totally, we still would stay with the 2/3 of our emissions from the clinker production. Now we have a twofold approach here, and I will tell you this. And just going back to the flow chart here, which many of you, of course, know, but just to remind you here that we start cement production with the raw material extraction. Of course, we make sure that the material is homogenized, because at the end we need a stable and homogeneous product. And as many of you know, the homogenization starts when you bring the raw material from the quarry to the plant. And the plant here is basically consisting of 2 parts. We have the clinker production. The clinker is the power horse in all cements, and it will also in the future be the power horse in all cements. And the characteristic phases of clinker are responsible for the ability of cement to harden when you add water. And this is unique. And because it's also based on the raw materials availability all over the world, it's a unique material that is produced in all countries, basically, on the globe. Now we have this high temperature process here, and I will come back to this in a minute, why it's so good. And we have heard from Hubert Grech here, what kind of fuels are used and how the substitution rates is what kind of alternative materials can be used in clinker production. But the next point is then producing cement from clinker, and the amount of clinker, of course, in cement is a very good measure of the CO2 footprint of cement. You could understand that the main CO2 emissions come from the kiln, and if you just optimize the content of clinker in cement, you could also optimize the carbon footprint of the total cement. And we have heard from Hubert Grech what kind of materials as secondary materials can be used here. And of course, this is depending a little bit on the availability of these materials in the respective region or area. To give you one example, here in Germany, we still rely to a high degree on slag from steel production, but to a growing extent, of course, to limestone and also to calcine. So the aim is to reduce here the cement with respect to the clinker content in cement. And most of you are familiar with the term clinker factor, which describes the amount of clinker in today's cement. So we have two indicators here. The one is the substitution, the thermal substitution of fossil fuels here in the kiln. And we heard from Austria that it is exceeding in Austria 80%. In our country, we are roughly at 72% today. And then the question is, how can we lower the clinker factor here? And in our country, the clinker factor is 71%, but there is still potential to further increase it. Now, the cement, of course, then is used in concrete, as you all know, where it's mixed with sand and gravel and water at the end. And then it hardens after a given time to allow us to construct buildings, houses, offices, and of course, all kinds of infrastructure. And at the end, concrete is going to be recycled and can be used back in clinker production, but also in the cement mill, which can play a role in CO2 mitigation, because concrete can absorb CO2, and we talk about here the fact is recarbonation is the technical term. Now, when we look at the different approaches all over the world, they are basically all over the world very similar. And if you were to read all these different roadmaps which have been developed by GCCA, for example, for the global cement and concrete sector, but also here for Australia, for Germany, for Europe, for the MPA, that is the Materials Products Association in the UK, but many others. Yeah, so this is not non-exclusive listing. And they all have the same approach, that namely, you look at the clinker first, you ask yourself, how can I produce clinker with as little CO2 emissions as possible? How can I reduce my clinker content cement, being as efficient with my clinker use in cement? And the next is, how can I use the cement as efficiently in concrete as possible? And finally, also, how can I use concrete as efficiently in construction? And I'm saying this, that the levers are very important, because as all the measures that we apply to the remaining CO2 emissions, which cannot be abated from clinker production, all this is then going to be based in the future on what is called carbon capture. And this is very expensive as compared to the other measures. So we have to make sure that we use all these different measures of efficiencies here in order to reduce the ultimate non-avoidable CO2 emissions from clinker manufacturing as much as possible. Just to conclude here, at that point, with the different pathways, we are talking about recarbonation, and those of you who are a little bit familiar with concrete, you know that recarbonation is a very natural process. So the clinker phases in concrete, as they are exposed to the atmosphere, they reabsorb some part of the CO2. Basically, it's the same process that we have, similar process that we have seen in the kiln, where you separate the CO2 from the material. Now, if you let it react after a given time, when the CO2 is reabsorbed, which is basically very important for the whole CO2 mitigation pathways that we draw. And I'll give you a picture at the very end. Now, if you go to the global scale here, what you can see here is a diagram of the Global Cement and Concrete Associations, and I was very happy to be able to develop these kind of numerics behind this. So, but what we have a challenge in many countries of the world. If you look at here, the y-axis goes from 2000 to 2050, and this is global. Here we would these are the CO2 emissions today, you know, roughly 2.8 gigatons CO2 annually. And you can see here that the blue line at the very top describes that the total emission on the globe are expected to grow if we were not doing anything. So the so-called business as usual scenario is anticipating, you know, still a huge increase in CO2 emissions globally. Why is this? The reason is that we have many countries on the globe which still grow population-wise, but also per capita. I mean, cement consumption per capita, because there are developing countries. And as you may know, that the development first starts with a decent infrastructure and housing, and there's still a need in many, many regions in the world. So if we were not doing anything, you know, we would end up here at a little bit more than 3.5 gigatons. Now the question is, how can we mitigate this? And you know, you come back to the value chain, as we call it. You ask yourself, you know, what are the efficiency measures in design and construction? How can we construct more efficiently? How can we extend the lifetime of buildings, for example? This all contributes to lowering the CO2 along the value chain. And another thing is, of course, how can we use concrete as efficient in construction? And you may have heard about high-strength concrete, which allow, you know, the building to be, the pillars, for example, to be thinner. That's one example, and allowing, of course, a high-efficient concrete. And then we have the savings in cement, and that is coming back to the clinker factor. And we heard from Hubert Resch what the Austrian approach is here, which is very similar all around the world. And you can see that it all adds up to a decent reduction of the CO2 emissions of the sector with respect to levers or pathways that are well known. That also includes the CO2 savings here in clinker production, which is basically increasing the thermal efficiency, and secondly, to take advantage of alternative fuels. And I will come back to this in a minute, what that means for the waste processing in the cement kilns. So, but nevertheless, to conclude and to give you the overall picture, there are going to be remaining CO2 emissions which we are not able to reduce with the conventional levers, even if we were to apply these conventional levers to an extent which is much more than we do nowadays. So we would go to the very possible, and still we have 40% of CO2 emissions that still need to be captured. And you can anticipate, you can imagine that the carbon capture is a complete new technology. It's energy intensive. We have CO2 as a material that we have to deal with. So it's a really new exercise for the industry. But you may know that quite a few of cement producers have embarked on this journey, to say so. And I think it's going to be good progress, and we will see in the years 2040 in Europe and 2050 globally quite a few cement plants being equipped with carbon capture. Now the question is, what kind of coming back to the fuel emissions, yeah, and there's where the different type of wastes come into the role. And I have to say that there are two aspects here of using alternative fuels as a raw material. First of all is the thermal effect, which is just substituting the calories, to say so, from fossil-based fuels by waste fuels. And the second, of course, is, and that also came clear from what Hubert Resch said from Austria, is we have the contribution to circularity here. We can avoid landfilling here, for example, or we can also make sure, that only materials which, cannot be recycled at the end and easily can be used in cement production. And we may also know, due to the pre-treatment and the selection of these wastes, as we heard a minute ago, the last presentation, we can make sure that the cement quality is not undermined. Yeah, that is the highest good that we have. We have no interest at all in being just a pure municipal waste incinerator, to say so. We are producers of cement, and we have still the aim is forever, having a high quality and environmental composition of cements. So that means, all the materials are well selected here and well controlled, to say so, as we heard in the last presentation, for example, with respect to input parameters. Now we have used oil here. We have alternative. We have used tires in our industry. We have then residues from industrial waste. We have residues from pre-treated municipal waste, for example. We have dried sewage sludge from municipal water treatment plants, which is in our country is a real blessing, to say so, because this kind of material was used as fertilizers on the fields outside, and nobody really was happy about this for very good reasons. And it's much better now. We first mechanically dewater the sewage sludge and dry it with low temperature, excess heat in the cement plant, and then it finally has a heat value of which is similar to lignite. And then of course we have fragments and sometimes also pure material flows coming from wood-based waste streams. Now, if you put it all together, you ask yourself, what is important with respect to its emissions. First of all, of course, is you avoid emissions in another place. That is another thing. But secondly, you have a high degree of biomass depending on the origin of the waste. Of course, waste oil is not biomass based, for the reasons that you can imagine. It's purely based on crude oil at the very beginning, and after its use, it's still fossil, of course. But tires, as you know, they have this from the rubber production. There's roughly 27% of biomass in it, and then in the mixed industrial waste and the municipal waste, you have various kinds of biomass. In mixed industrial waste, it can be up to 30%, in the municipal waste even up to 50%. Sewage sludge and waste wood here, of course, by definition, is pure biomass. So this is, of course, something which is of great help here, because as you all know, biomass is CO2 neutral. And if you draw the overall picture here, of the pie chart, what you can see here, that in our country here, maybe that is complementing the presentation that we have heard before. So our 50% of the contribution here is coming from industrial and commercial waste here, roughly. The composition here is basically plastics and cellulose, paper, and board. And then we have the remaining part here, and I'm not going to read this for you, but the main question, of course, is how is this to be seen with respect to its biomass content? So, and that is quite significant, and therefore there's a twofold incentive for the industry to use biomass-containing waste. First of all, is to substitute fossil waste as such, by heat, and contributing to circular economy. And the second, of course, is to take advantage of biomass. The use of biomass, as you may know, is regulated under European law. You might have heard about the RED I and RED II Renewable Energies Directive. It's first, second, and third version. And here it's strictly controlled, what kind of biomass can be used. And to say it in a few words, biomass must be assured to be from sustainable sources, to not incentivize the use of precious biomass, which should not be used as a fuel. So it's all under strict regulation, to say so, not only from the for example, from the trace elements point of view, like we heard from Mr. Gresch, but also here from the question, how can biomass be? Now, what is good in the cement kiln, and those of you who are familiar with cement production, know that it's basically the cement clinker making process is the material transformation process. So we start with the raw material, we heat it up, and we get another material which is called the clinker. And in between, we have a mineralogical transformation. And we need some elements in there, and if they are not in the raw material, we have to add them to correct finally. And we need not only the calcium oxides that I've been talking about, and the silica oxide, from the clays, but we also need other elements from clay minerals like aluminum oxide. But we need also iron in order to form sufficient, as we call it, melting phase in the kiln to allow this transition to actually to happen, you know, from limestone to clinker. And many kilns are poor, many raw materials at cement plants are poor in iron, and iron has to be added, and therefore it's a win-win situation when, for example, tires are used which have a high concentration of high content of iron, you know, in the steel belt around the tire. So it's a win-win situation because all the material is basically, you know, used for clinker formation. And this is on the other side, and Hubert Brecht has underlined this. It's on the other side, it's a need because all of the materials are, you know, kept in the clinker. They stay there. There's no extra waste stream to be generated. We have to make sure that these materials are pre-treated or controlled with respect to their trace element concentration, for example, to the degree as we have heard from Austria, for example. Now, a case study here for sewage sludge is very interesting. It's more than it's roughly 2/3 to say so organic components, 2/3 is biomass, and the rest again it's silica that we are in need of, and it's calcium that we are in need of. And we have aluminum and iron that we are in need of in order to form the clinker phase. So again, you know, this is 100% being used as a fuel one hand side and as an raw material on the other side. And therefore, in many cases, we use the abbreviation AFR, alternative fuels and raw materials, so that fits all in this context. This is the development in our country here in Germany. So we are just barely exceeding 70% here. We have heard from Austria. To my understanding, Austria is the most advanced country in the world with respect to thermal substitution. It is also, I think, you know, part due to the fact that it's from the government. It's kind of controlled at the one hand side, but on the other side, it's also, you know, supported because it avoids landfilling. Here, you know, my focus was on the CO2 efficiency, and just to underline, you know, that these materials, you know, even if they contain biomass, they're not just burnt, yeah, but they're really used with a high efficiency for clinker formation. And you can see that the efficiency in cement plant is among the highest of many other industrial installations, for example, with respect to power plants or new or existing one, but also to plants that produce alternative fuels, power plants, and waste to energy and waste incineration plants. Of course, you know, this is very much depending on the local situation. There are also plants in the meantime which have a higher efficiency if there is waste heat coming out. Now, why is the efficiency of a cement plant so high, and why is it really, you know, does it make sense to use, for example, alternative fuels also containing biomass? The reason is that we have a countercurrent system here. If you go, you know, from left to right, you would say you go from the let's see, from after the quarry, the material is fed to the kiln. And here you have the clinker. And the material, you know, is then entering the kiln. It's heated up in the counterflow of the hot gases, you know, from the combustion. It's going up here to almost 1900 degree gas. 1400 degrees material temperature. And if you go the other way around here, you know, you can see here the combustion gases. You know, they start in the kiln here to be ignited. They are preheated, ignited, and you have combustion gases which are almost 1800, 1900 degrees centigrade. Because the combustion gases are then, you know, going this way, and the material is going the other way here. This is the material curve. You have always a strict counterflow, and you may have seen cement plants, which is so-called cyclone preheaters, in which each stage, you know, there is an intimate mixture of gas and material. This is the basis for having an extremely high efficiency of clinker production. And if there at the very end, there is some temperature left here, you can still use this for waste heat recovery, but the efficiency at these low temperatures, of course, is not limited. Now, just one side comment here on the residence time, which is underlying the uniqueness of a cement kiln, in particular when it comes to the use of alternative fuels. You can see here, that in the kiln we have a gas residence time, and that is what comes from combustion, which is 10 seconds here in the highest temperature part, but still 3 to 4 seconds in the part that is exceeding 1200 degrees or 850 to 1200 degrees. And then there is still the cooling phase here. And the material is the same, it's the same, means some very long residence time. Of course, the material takes much longer, and it can even be 30 minutes till the material comes from one end to the other. And that is that we have a complete combustion here. We have high residence time, but even persistent organic materials are completely decomposed, which is of course not the case for most of the biomasses, but just to draw up the whole picture here, it's a unique facility here for applying alternative fuels to the industrial process. And then I'm coming with this slide almost to an end of my presentation. This is the roadmap of our country here in Germany, just drawing the complete picture. We have 20 million tons of CO2 in as starting point, 2019, 2020. And you can see here, these are the abatement levers, saving in construction, and saving in the other parts here. And what you can see here, the savings in clinker is just the further anticipation of using biomass in clinker production through the use of alternative fuels. Now, why is this so limited, so small? The reason is that we are already applying, a high degree of alternative fuels, which respective content of biomass. If you draw this picture for countries where you start using alternative fuels, the contribution here is much bigger. So it depends on the reference time here, and the question, what was the substitution rate at that time? Now, I'm not going to repeat what I've shown you. The clinker factor reduction here is, and then at the end, of course, the use of carbon capture and the subsequent utilization of the CO2 or its storage. I talked about the recarbonation, which is a natural process, and at the end, you end up theoretically with zero CO2 here in 2050. But the nice thing is that if you capture biogenic CO2, then of course, you have a negative emission to say so. That means you have carbon removal from the atmosphere. And in our case, Germany, that would end up in 1.6 million tons annually biogenic emissions, carbon captured and stored. So that means there's a contribution of the carbon capture process to lower the overall concentration in the atmosphere. And we need this here because, of course, the whole value chain is, of course, theoretically it's 100%. But if you go to a single plant, it's not really 100%. The availability of the capture devices is 90–95%. So there's always a need to capture this remaining part. Now, I think I can be fast in my conclusion. I think from what I've said is you can understand that decarbonization is top priority in the sector. We have CO2 emissions from the raw material and from the fuels. And here you have seen that we have different levers that we can apply in order to reduce our CO2 emissions. You've seen the different roadmaps, and you have also seen that. I think that is the theme of this conference here, that the emissions from the fuels can be reduced, particularly using waste-containing biomass. It is not only that we can have a CO2 aspect here to be covered, but we also, of course, will contribute to circularity as we have heard it in my previous presentations. I think I can then stop with the rest of the summary. I understand that the presentation is going to be made available to all of you who have an interest. And of course, I'm available in the panel to answer your questions if there might be any. Thank you very much for listening. And with this, I stopped sharing my screen. Thank you.